Welcome to Team 33's interim presentation. I'm Kimberly Kerr, and I'm here with my teammates Jack Decker, Crystal L. Ashkar, Noah Hilbig, Gina Schmidt, and Joseph Cabrosi. Today we will be presenting an in-depth analysis of the Mainstays 4-slice toaster oven. The Mainstays 4-slice toaster oven is a popular, convenient miniature kitchen appliance utilized in heating up food with an estimated production volume of 50,000 to 75,000 units annually, as determined via market research. This simple appliance is used in the day-to-day lives of many people across the world, whether it be within a corporate kitchenette, college dorm, or within a family's kitchen, as it is both an affordable and convenient option. For our purposes, we will be defining our primary customers as households and our secondary customers as corporations. Breaking down the components in the Mainstays toaster oven, we utilize an exploded view of the product to give a better idea of all components being considered as well as their relative locations within the assembly. It is important to note that we consider the bottom hinge, heating elements, and control knobs as black boxes, meaning that we will not be further analyzing the smaller components within these components for redesign.
This is our fast diagram for a functional analysis that describes the tasks that the toaster oven performs. Our main functive branch is related to food preparation, which is the toaster oven's main objective. Next, we're looking at two different assembly sequences that both move from left to right. The first one starts with the bottom plate that the assembly is built off of and ends with the outer plate. The second one includes more sub-assemblies, starting with a heating element assembly that consists of the heating element guard, inner case, and heat sink plate. The overall assembly ends with the outer case. As you can see in our sequence comparison chart, we decided that sequence 1 was more ideal due to its ease of transferring and handling and ease of fastening joints.
A functional mapping matrix serves a variety of purposes in design for manufacturing, namely ensuring that each product function is completed by a component. For example, the heating element on our toaster works to generate heat and speed up the cooking process. This matrix also gives insight into design optimization. We can see what components on the toaster can be combined or redesigned to improve efficiency, reduce cost, or improve manufacturability. If you go to the next slide, you can see that the handle has both a plastic and a metal piece. This could be an opportunity to combine the pieces into one, as they both serve the same purpose, which in turn would reduce the amount of pieces on the toaster and reduce cost of manufacturing.
This is our BOM for our part. The annual production was assumed to be around 75,000. The parts of this product were mainly assumed to be stainless steel unless it could be otherwise proven. Stamping would make the most sense for most of these parts for the manufacturing processes. The material cost was derived from estimating the mass of each part. The processing cost was derived from the estimated time and cost it would take to stamp each part, if that is the manufacturing process. And finally, the tooling cost was derived from rough estimates of the cost of each machine and how much they produce in a payback period. On the next slide, you can see that the total unit cost comes to be around $17, which is about 50% of the average market price for these appliances.
To determine which parts are best suited for DFMA, we used a quad chart. Our quad chart compares the functional importance and manufacturing costs of each part in the toaster oven. Low cost and low important parts are considered for elimination, as are the low importance, high cost parts. These include the handle plastic, foot stopper, stabilizer brace, bottom plate, and outer case. The low cost, high importance parts can be kept as they are: the control knob, control plate, foot, handle plate, handle metal, door spring, and top door lid. The parts that we decided to consider for DFMA are high cost and high importance. These are the door glass, heating element, bottom hinge, inner case, heat sink place, back panel, heating element guard.
Here's our product family design chart. for FDT, we had similar to customer groups being the heat coils, insulating walls, countdown, alert users, insulating heat, and directing the tray. The different functions between the customer groups include holding large volumes of food, holding large masses of food, showing the food, and cooking fast. In our CCT chart, our platforms identified with the heating element, inner case, back panel, outer case, control plate, control knob, heat sink plate, and our modules with the inner case, outer case, back panel, bottom plate, door glass. The CAD for our primary group, which is the households, is seen on the left. As you can see, this is just the CAD as it was, with no modifications made to it. The modifications made for the corporate usage was including another little indent in the inner case to allow for a second tray to be placed there, along with a stainless steel addition where the glass went initially to create for better insulation and more efficient cooking.
For assembly of both applications, we have determined that the first 10 steps can be assembled together. After applying delayed differentiation to simplify the process for 2 modifications, we can simplify the assembly sequence. This concludes our presentation. Thank you for watching our video.